let me introduce Simon Meyer to you. So he's a professor of interaction and communication-based systems at the University of St. Gallen. And with his research group, he explores interaction among devices and people in ubiquitous computing environments. He's a seasoned Web of Things expert who says was there from the beginning, right? And yeah, it's a pleasure for us to having you here. So the floor is yours. So I will stop sharing my screen.
Thanks a bunch, Cristiano.
Yeah, no problem.
I'm unsure if seasoned is something good in that sense. Let me share.
Right.
Let's hope. Okay. Welcome, and I'm just getting my controls ready. I hope that my internet connection is going to hold up. I'm sitting here in Cesena right now at the University of Bologna, and I was quite looking forward to giving this talk. And I must say it was quite a bit of a challenge to bring basically those things that interested me about this project that is now running for 3 or even 4 years almost, to bring this into 20-30 minutes. So I called this talk IntellIoT loves WoT, right, for kind of obvious reasons. And as all the times I get to present, but this is not my own work, right? So I have a few people on here who were mostly contributing to this. And if you now see my transition, then everything works. Ege, Cristiano, yes?
Everything works.
Okay, perfect. Yeah. So I'm Simon. I'm leading a research group on interactions between agents and non-agents, between agents and artifacts. I myself, I come from the pervasive computing area. I was spending a lot of time with Matthias in the past when we were doing our PhDs. And I focus nowadays on autonomy, on interoperability, and on human system interactions. And this is who I work with. So this is my current research group. You can see from this slide that there's quite a breadth of topics in there. These topics, however, come together when we look at the interaction of people with ubiquitous computing environments. And to me, the Web of Things from its beginnings, from back in the days, over the focus on hypermedia, over the increasing focus on REST, specifically hypermedia, on advanced or novel description formats for things like W3 C WoT thing description. This has been a beautiful interoperability journey, right? And I'm traditionally skeptical about interface definition languages. I'm a big fan of late binding, and I'm a big fan of resolving things at runtime and not compiling against IDLs. And these things, to me, these are all instruments to enable flexible interactions in such ubiquitous computing environments. So we are working in a diverse range of topics, and here is a quick overview of recent papers. So just that you see what we are doing other than worldwide autonomous systems. So this up here is our focus on, and I can get a laser pointer. Excellent. This is our focus on ubiquitous computing environments, on robots, on eye tracking applications, also in interactions directly with things. So I'm a big IoT fan, if you want. And down here, those aspects that I'm going to be more emphasizing today, specifically in the very end of this talk, I'm going to be emphasizing this paper down here, which will be presented in a month at the Autonomous Agents and Multi-Agent Systems conference in London. So this brings me to my talk. I'm here to report about a project that we have been working on with lots of other people, right? As these European projects go, we are by far not alone. This was a RIA, so this was a research and innovation action. So this was not a research project. However, as a university, we obviously emphasize the research aspect. The goal was, from our perspective, from the University of St. Gallen perspective, to integrate web-enabled industrial devices and autonomous agents within multi-agent systems. Okay, so this is what we wanted there. We successfully deployed 2 use cases in this context, one in autonomous agriculture and one in industrial manufacturing. And my personal, so here you see these 2, right here, over here you see an autonomous tractor in Steyr in Austria with one of our partners, and down here you see a Siemens robot that were deployed in 2 different use cases. My personal motivation in this project was to drive interoperability. This is also what brings me close to Web of Things, right? to enable decoupling of different services, so to increase the flexibility of these deployments, and ultimately, and this is, to me, this is the same story. To me, these two ideas lead towards increasing autonomy in such industrial, in this case, but in such Internet of Things environments. How can we have these environments? How can we have entities in these environments, some call them agents, behave more autonomously? So as an introduction, I'll show you the most recent videos. This is the video from last week. The most recent videos as outputs of this project. What you're seeing here is not the Postman interface. That's not the interesting part. But what you can see here is our successful integration of an autonomous agent that drives a tractor through W3C Web of Things thing descriptions. So one question that I don't know is why the front left wheel doesn't move, so please don't ask me this. But this tractor is, you see, it's up on the scaffold, right? So it's not actually driving, but it is following GPS coordinates. So this is enabled through things that expose WoT TDs. Some of these things are a tractor controller, so the driver of this tractor, a waypoint service for resolving the GPS coordinates, for giving us the next waypoints, for resolving fields to be harvested to GPS coordinates. An AI service, this is a local service that enables the tractor to go around obstacles, a journaling service, and a human-in-the-loop service that kicks in when the AI service fails. Okay, so this is the, and there's many more, right? If you want to look at all the TDs that are active in this scenario, then down here is a GitHub repository with all our IntellIoT TDs that you are free to browse. Okay. These TDs are then exposed via a platform for agents and artifacts that we refer to as Yggdrasil. I can show you a quick demo of how this would work. So over here you see the Yggdrasil platform, a specific workspace in that platform, and this workspace exposes, for instance, the action affordances make artifact, which tells us that I can create an artifact at this workspace. Some such artifacts are already created. One of these is a robot in our laboratory. So if I go and dereference that robot, I get a thing description of that robot, and this enables me to steer this robot. The actual TDs that we were using in IntellIoT, the tractor TD is linked from here, and all the other TDs are available, as I was saying. Now, what is interesting about our project is that what we did was we discovered these TDs then at runtime. So they were registered in this platform at runtime, and then we discovered them through a no-code development environment. So our idea here, our challenge, our goal was to enable non-programmers to be able to program agents against W3C WoT TDs. Okay, so we call these domain experts. This could be an industrial engineer, it could be a farming engineer, but it's someone who is comfortable with the domain, right? Who's comfortable with the terminology of GPS, of driving a tractor, of harvesting, things like this. But this person is not comfortable with coding, and I'll show you what we did there. And finally, at runtime, an operator then issues goals, a goal such as harvest field 5, and these goals are taken up by an agent. And then the agent takes over the coordination between these different things up here. So the agent will say, hey, tractor, go over there. And then the tractor will try to go over there. If it doesn't, it will tell the agent, I have a problem in my field of view. There's a tree. The agent will tell it, go ask the AI service what to do. The tractor will go to the AI service to ask what to do. And if it's successful, it can circumvent the tree. If not, it can escalate to the human-in-the-loop service. In this case, a partner of ours opens a virtual reality connection, and a robot and a human actually drives the tractor around the obstacle. So there's many more components here that I'm not focusing on. I will show you the main points from the paper about the no-code environment in a few minutes. And we have an extended abstract at the AMAS conference in London in a month on this overall architecture, so on our overall proposals towards this architecture. And I think the slides will be shared, Ege or Cristiano, and the video anyway. So I'm transitioning from the agriculture to the industrial use case, the second interesting use case in this context. This looks exactly the same as before. This was our intention, right? That they on the system level, that they're on the architecture level, that they look homogeneous. In this case, what we do is that somebody creates a goal of engraving something into a wooden plate, and then this wooden plate should be selected. An inline machine learning system tells the robot where to grab this thing, which is not our component, but this is somebody else. But you see the camera over here at the robot gripper. And then this item, this wooden plate in this case, is selected. It's put over here into the engraver. Then this custom designed by one of our colleagues, custom designed platform over here will insert it into the engraver or into the laser engraver, and then this thing will start engraving the text that we wanted. So essentially, this is again the same storyline as before. The things expose WoT TDs. It's different things now. It's the robot controller, the engraver, the grab spot service, again the journaling service, and again a human in the loop service. They are again exposed via the same platform. They are again discovered by a no-code development environment. They are again programmed against by a domain expert. And at runtime, an operator issues goals. Just this time, the goal is like engrave the text IntellIoT at location XY. Okay, so this is what here you see the engraving now. So this is the introduction, and both these use cases bring together lots of different devices, and these lots of different devices and the different. I must say, in the context of this project, the different non-functional requirements by our project partners. This was what was driving our main insights, I would say. And I'll share some of these now. So what I will do next is I will cover the following components in the project that I would like to share with you, and that I would like to get maybe also your feedback from about, or as already discussed with Ege a few weeks ago, see where these align with discussion that you've been having in the W3 in the WoT. Sorry, I'm not used to this. WoT in the WoT 20. So first is the management of W3C WoT TDs in our hypermedia mass infrastructure. The second is I'll show you the no-code development. The third is what we together with Ege, I guess we called this WoT TD negotiation for lazy deployment in the context of this project. And then two small points on journaling of agent artifact interactions and on WoT TDs in the context of performance theory. Okay, so I'll start with the first one. This is the overview of the industry use case, of the manufacturing use case, but it's similar for the agriculture use case. So we have our devices somewhere. These can be big devices like robots, or small devices like this mirror card, which is currently being integrated into the use case, but which has been running in our laboratories for some time now. So this is a battery-less device that we also hide behind a thing description. Then we have our platform, and these devices register their thing descriptions and keep their thing descriptions updated at the platform. If there's no binding yet, we can also handle this case. And in fact, I'll get to this specifically. So then so device and service register, then at deployment time or at configuration time, at engineering time, the domain expert opens this no-code environment. The no-code environment goes to the platform, fetches the TDs, creates blocks from these TDs that the domain expert can use to program, and then deploys the created agents. So these are agents programs in the dialect of the agent language. These agents are then deployed to the platform and then run over there. And then they keep running until they get something to do, like humans, right? Like humans. We toil around until somebody tells us something to do, some goal to achieve. This comes at runtime. A user opens up the IntellIoT interface, configures a goal, like engrave IntellIoT here, sends this goal to the platform. This goal is taken up by an agent at the platform, and then the agent accomplishes this goal according to its plan that was configured earlier, and using these devices up here. So these devices are used by the agents. And if a device is not bound, so if we only have a TD model or a thing model at this point, then we have a mechanism together with Siemens that binds devices only at runtime. We call this edge orchestration, and I'll get to it. Finally, interactions between agents and artifacts are journaled. These are journaled in a distributed ledger system, but it's not at all interesting, or to me, I should say, it's not at all relevant that this is a distributed ledger. This could be any journaling system. But the point is that the agent will say what it wants to do. The thing says what the agent told it to do, and in line with this, we also register the TD that is active at runtime, right? Because this also becomes a relevant part of the journaling in this case. So the first aspect is the center. I start at the center at this thing down here, the hypermedia mass infrastructure. Then I will show you the end user IDE down here. Then I'll go into the lazy deployment, and then I'll briefly cover the journaling. So here's the infrastructure. This infrastructure has been, we published a little bit about this already in the past. But what this mainly does is it supports the creation of hypermedia multi-agent systems following the Giacomo meta model, which is a meta model that comes out of autonomous agents research. For us, as a practical application of this, the main things that we need to take care of is to expose the agent's environments, specifically things in the agent's environment, and also to deploy and run the agents themselves. So we need quite down to earth. We need a scalable runtime for agents. As a bit of background knowledge, this research has, of course, the research on autonomous agents, multi-agent systems has, of course, been going on for decades, but only recently have we started considering the web as a prime environment for these agents, and this brings interesting problems to the agents community that were traditionally not there. Right, classically, it's a different thing whether you know what your system is going to be looking like at runtime, like in a traditional agent container, or if you don't know what it's going to be looking like. And this brings interesting challenges. One expert in multi-agent systems has recently called the web chaotic, and I think I completely understand what they mean. So I didn't know that the web was that chaotic, and I love that statement. So this is what Yggdrasil supports: the execution of computational artifacts, agents to instantiate artifacts. It exposes interfaces to these artifacts. These include workspaces, so they include agent-oriented abstractions of how we can arrange things in the agent environment. And it also generates WoT TDs for these artifacts. And of course, it also complements its internal artifacts by WoT TDs for external device services. So this is the registration process that I was talking about before. The resulting environment is represented in RDF, and the infrastructure is compatible with search engines for the W3C WoT. For instance, a search engine that we published a few years ago, but nothing huge, but an engine that allows approximate searching for things in the web of things. Our proposal is that this can be a blueprint for a W3C WoT TD-based system that may include autonomous agents, providing a runtime and providing the environment, the required environment abstractions. Second, sorry, I don't have my own office here, so it's a bit loud around me. The second aspect I want to go into is the no-code development for multi-agent systems. So here's this abstraction that you have up there. We created this system over the past year. And what this can do is it can be used to configure and deploy hypermedia multi-agent systems. And we've recently extended this also to organizations of these multi-agents. What is interesting for this group is that our functional blocks are automatically generated from W3C WoT TDs, and then they map to abstractions in the agent speak language. So they map to abstractions in concretely the JSON language, not to be confused with JSON, right? So the JSON with an A in there. Which is a language for programming procedural knowledge of agents. Now, what happens there is at runtime, the web-based, or at deployment time, at configuration time, the web-based IDE fetches TDs from Yggdrasil and then generates these functional blocks. And then these functional blocks are composed by the domain expert, and then they're deployed to Yggdrasil. Our underlying assumption, somewhat verified assumption, but to some degree still hope that underlies this, is that an agent abstraction to program these environments is a better fit for humans, for non-programmers, for humans to program applications in these environments. The idea would be that it's closer to how I think anyway, that I would delegate tasks to agents rather than programming loops, for instance. So this is the underlying point here. So with this we can resolve protocol bindings only at runtime, which is pretty cool, and I'll get to this next. And our proposal is that this could be used to create agents based on W3C WoT TDs. We did a limited user study with this, where we had users who were programming for the first time, and they accomplished amazingly much using this abstraction. So I'm not claiming that this is the hope for end user development, but it might be an idea to consider agent programming for end user development. Here's the paper that documents this, and over here is a quick view of what this looks like. Quick insight on what this looks like. So let me just show you the part back here. Wait. Hey, now here we go. So this is what the agent speak code would look like, or the JSON code would look like, and then here's this running a task in our own laboratory. And in a second, over here, we will see the blocks that form this. Right. So this is formulated as if I was talking to a colleague, right? When the agent decides to achieve bring block, then it always says bring block, and then it asks the thing SpockBot, this is this bot down here, to wheel control. I admit that this is a bit tough, right? With an input of object access speed duration. Okay, but I hope that you see the idea. This is basically trigger action rules that we map to from W3C WoT TDs. My next point is W3C WoT TD negotiation. Our partners in the project desired that they are able to deploy services only as late as possible. Their main issue is that they try to optimize the industrial edge, right? So they try to bring for instance, at runtime, well, first to undeploy services that are not used, and second to at runtime deploy services in a way that is optimal for their own infrastructure, maybe regarding resource use, maybe regarding latency, but really to us, whatever non-functional property they would like. And we took this up, and therefore we supported the usage of WoT TD templates from version 1 and of WoT thing models for version 1.1 for permitting late binding of edge orchestrated services. Concretely, this takes the form of the IntellIoT edge orchestrator. This emits W3C WoT thing models, so I can program against the affordances in this, but there are no protocol bindings. And then I can program my agents using our Web-based IDE against these thing models. But at runtime, the deployed agent will inline request the service to be bound from the edge orchestrator, and the edge orchestrator will then decide how to best deploy the service and then return a protocol-bound thing description. The proposal is to investigate W3C WoT TD negotiation a bit more. What our partners were also proposing in this context is that we could also negotiate parameters of machine learning systems, so also late binding in that sense. And of course, also security parameters could be bound in this sense, right? I request this functionality, but I don't require security. And maybe I get a different deployment. So to have an intermediary in there, perfectly in line with the web architecture, so to have an intermediary that brokers these requests. And overall, we could have any non-functional parameter of a thing or service to be used in this negotiation process in this sense, which I found quite interesting. This brings me to the last two aspects. We've created a journaling system for agent artifact interactions, so we have a prototype of this. The purpose of this is to monitor auditing, root cause analysis, and possibly payments processing for using of W3C WoT TD services. We record the concrete exchange messages according to the TD binding, and we also record the service descriptions that are effective at runtime, which we think is rather makes sense. In our project, we implemented this using a distributed ledger, but of course, any other system can be used for this. Right? So we are not bound to DLTs. And the final aspect that I have is W3C WoT TDs in the context of affordance theory, together with another project, with the HyperAgents project over here. We were investigating affordance theory in the context of the guidance of interactions of autonomous hypermedia clients. And what we did in a paper that will be presented in a month is that we proposed the introduction of signifiers as a first-class abstraction in web-based multi-agent systems. Why we do this is that this would allow us to differentiate between signifiers and affordances to allow runtime adaptation of exposed IDLs. So concretely, what we have proposed in that paper is that we have signifiers, TDs in the end, that are adapted at runtime to agent goals and also to agent abilities, including agent cognitive abilities. So one way how we could do this is here you see two such signifiers, and the one on the left is created for an agent that implements a procedural reasoning system, so BDI architecture specifically that is based on a PRS. The one on the right implements the same functionality function-wise or outcome-wise, but this time for an agent that is a strips planner. So over here we have strips planners, over here we have BDI agents. And the interesting, or the relevant difference between these two is that a planner, of course, requires things such as preconditions and effects, right? Where we use PDL for describing these down here. While a BDI agent, if I give this agent precondition and effects, it cannot do anything with this, right? So this one needs things such as abilities, such as properties down here. Okay. So this is the overall idea here. So to enable a deeper runtime negotiation, if you want, runtime adaptation of TDs to the agents that use them. A bit like if you think about a human abstraction, a bit like a sign that always shows its content in the language that you understand best, right? You at runtime understand best, and not just in English all the time. So this brings me to the end. The last thing that I want to mention is I would like to introduce a new W3C community group. The group is called Autonomous Agents on the Web, and this is an outcome of a recent DAX-Tool seminar. Some people on this picture you might recognize. So recently we have a DAX-Tool seminar that was bringing together the traditional fragmented communities of WoT, of web architecture, autonomous agents, multi-agent systems, semantic web. And this one outcome of this seminar was the W3C community group. The idea behind this is that it seems that what we are enabling with W3C WoT TD and other systems, this interoperability and the flexibility that this interoperability gives us at runtime is an ideal fit to more autonomous behavior by entities at runtime, not just by people, but also by artificial agents. So our proposal here is to join forces to drive interoperability and drive autonomous behavior in a web of things, and to make this worldwide through the web and make this more autonomous through multi-agent systems and autonomous agents. And I believe that this should be my last slide, so I'll leave this slide on. As an overview slide, probably this one is better suitable. Let me take this one, and I'm happy to discuss anything